Hello everyone, in this video we are going to discuss another type of first order first degree differential equations which are called exact differential equations. Before we move on to the idea of exactness for a first order first degree differential equation, recall that a first order first degree differential equation looks like this in general. dy by dx equal to some function of x and y. For discussing the idea of exactness, it would be preferable to rewrite this first order first degree differential equation in this alternative way. We can rewrite a first order first degree differential equation looking like this in the following manner. A function of x and y, say mxy dx, plus another function of x and y with dy equal to 0. It's going to be more suitable for us to rewrite any first order first degree differential equation in m dx plus n dy equal to 0 format to assess whether it's exact or not. Now, before we begin with the idea of exactness, let us look at the following illustration to understand the motivation behind the introduction of this category. Let's look at the differential equation x dy plus y dx equal to 0. Now, this differential equation has been put in this form: m dx, m is y here, m dx plus n dy equal to 0, n happens to be x. Now, if we look at it in this form, then we can rewrite this differential equation as dy by dx. I can take dy below dx, dx below dy and rewrite this differential equation in the following manner. Now, since it's a separable equation, we know how to solve it. We take terms involving y with dy and terms involving x with dx and integrate both the sides. So here we get a log y, here we get a log x, and then we can add the constant of integration here. Now when we combine logs, it's easy to see that the solution takes the form xy equal to some constant. Let's call that constant as c. So solving this differential equation was very easy because it turned out to be a separable differential equation when we looked at in the general form dy by dx equal to fxy. Now, alternatively, if we do not rewrite this differential equation in the dy by dx format, it is easy to see that this left-hand side, the expression on the left-hand side, is nothing but the total or the exact derivative of the function x times y. Because the derivative of x times y is going to be obtained using the product rule. If we expand it, it's going to be x times dy plus y times dx, because product rule says first function derivative second plus derivative first into the second function. So if we look at this minutely, then we observe that the left hand side is nothing but an exact derivative of an expression involving x and y. So this differential equation can be rewritten like this, and such differential equations, we know that the d, the differential and the integral operator are inverses of each other. So we can straight away integrate both the sides after rewriting this differential equation in this format to obtain the answer. The integral of derivative of x and y obviously happens to be xy, and the integral of 0 is the constant of integration, which we can denote by c. So we did not have to go into separating the variables and then doing two separate integrations on both the sides to land into the same answer. You just observe that the expression given on the left hand side happens to be an exact derivative, and you make that exact derivative and just integrate both the sides to get the solution in one line. So such differential equations which happen to be of this category are termed as exact differential equations. So now we are in a position to introduce the idea of exactness. A first order first degree differential equation is said to be exact. Suppose my first order first degree differential equation looks like m dx plus n dy equal to 0. Then this is exact if and only if I can write the left hand side expression as d of some function of x and y. So whenever the left hand side can be expressed as an exact derivative of some function of x and y, we call it an exact differential equation. So that means this is exact if there exists a function phi xy such that my m dx plus n dy can be written as d of phi. So whenever this happens, this differential equation is going to be exact, and if it doesn't happen, then it's not going to be exact. But there are ways of making non-exact differential equations exact, which we'll be discussing in subsequent videos. But let's take one more example to understand this idea better. Let's look at this example now. Suppose we have y cube dx and 3xy square dy equal to 0. Now this equation is in the form m dx plus n dy equal to 0. It's a first order first degree differential equation. This would be exact if I can identify some phi such that this left hand side expression becomes d of phi. Now if you observe this minutely, then you are able to see that it's nothing but d of xy cube. Using the product rule, it's very easy to verify it backwards. It's going to be y cube into the derivative of x, which is dx, plus dy into 3y square, which happens to be the derivative of y cube, into x as it is. So this is how you identify, you verify your calculations backwards. Using product rule, it's easy to see that whatever is written on the left hand side of the given equation is nothing but the total or the exact derivative of the expression xy cube. So you can write this differential equation in this format, and once this is the case, that you are able to identify what phi is so that the total derivative appears on one side and the other side is 0, it's just a matter of integrating both the sides to obtain the solution. When we integrate, integral and d are inverses of each other, so it's actually going to give me only xy cube, and here I get the constant of integration, and that's the end of the problem. We are able to identify solutions of exact differential equations in just 1 second, provided we are able to identify what phi is. So that means the challenge in solving exact differential equation actually lies in looking for a suitable phi such that my m dx plus n dy takes the form d of phi. Now this is not as easy as it sounds. These two examples which I have taken are the easy ones where it is easy to see what phi serves the purpose. What is that phi such that d of phi becomes m dx plus n dy equal to 0. In advanced problems, it's not going to be easy for us to identify phi. So what we do in such situations is we use certain theorems which are based on some knowledge of partial derivatives, which I'll be skipping for now, because assuming that you do not have any idea about partial derivatives right now, or partial differentiation theory right now, I'm going to tell you two short techniques of, first of all, verifying whether a given equation is exact or not, and once it is exact, I'll tell you a simple procedure of finding the solution without going into the hunt for the function phi. So let's look at what is termed as criterion for exactness. How do you check exactness to begin with? Because looking for a phi or going on a hunt for phi without knowing whether such a phi exists or not is going to be a futile exercise many times, right? So it's always good to have this prior knowledge of exactness for the differential equation before you go for your hunt for phi. So come back to your original equation. It's m dx plus n dy equal to 0. This equation is exact if and only if the following happens. Whatever function is appearing with d of x, take its partial derivative with respect to y, and whatever function is appearing with d of y, take its partial derivative with respect to x. If these partial derivatives happen to be equal, then the equation will surely be exact, and if they are unequal, then it's not going to be exact. It's an if and only if statement. Equality of partial derivatives, equation exact. Equation exact, equality of partial derivatives. So once you see your differential equation and you check for equality of partial derivatives, if the partial derivatives are equal, then you can be sure of exactness, and then you can either go for the hunt for phi, which again is not going to be very easy all the time, or you can adopt an alternative method which I'm going to discuss right now to find solutions of exact differential equations. So whenever you see any differential equation, let's come back to our previous question. We took y cube dx plus 3xy square dy equal to 0. Let's look at this and see whether it is qualifying the criterion, it's satisfying the criterion for exactness or not. M dx plus n dy equal to 0. So this is our m and this is our n in the question. For exactness, what should happen? Del m by del y should be equal to del n by del x. Now by del m by del y, we mean the partial derivative of m with respect to y. That means you have to differentiate m with respect to y, treating x as a constant. Whenever you differentiate partially, you differentiate with respect to the variable, treating everything else as a constant. So when you talk about del m by del y, you have to differentiate y cube with respect to y, treating x as a constant. So it's going to be 3y square. And del n by del x. So here for del n by del x, you have to treat 3y square as a constant, because when you are talking about partial derivative with respect to x, everything involving y is a constant. So del n by del x is going to come from here as 3y square only. So 3y square is like a constant, x is attached to a constant, so del n by del x will be 3y square. Both of them are equal, so you do have exactness, and that's the reason you were able to identify your phi, because the given equation was exact. You were sure that the equality of partial derivatives is there, so you were sure that such a phi exists, and hence you go for a hunt for phi and you finally land into that phi. Sometimes what happens is that even when you're sure that exactness is there, you verify the equality of partial derivatives and still you are not able to identify what phi is, then there's a theorem which saves you. That's called rule for solving exact differential equations. So they should be exact to begin with. You should know that they are exact through the equality of partial derivatives. Then what you do is, so suppose your m dx plus n dy equal to 0. So n is a function of x and y, m is also a function of x and y. So I'm writing that here repeatedly. Even if I miss writing x and y, it's understood that m and n both are functions of x and y. So suppose this equation is exact. Then to solve it, find, number one, you integrate m with respect to x, treating y as a constant. So you find out the integral of m with respect to x, treating y as a constant. In the second step, you find out the terms of n which are not involving x. This n star denotes where n star denotes the terms of n not involving x. So you are to look for terms of n which are not involving x and then integrate those terms with respect to y. And then finally your solution is given by the two integrals that you have obtained in step 1 and 2 respectively. Add them, equate them to a constant, and that's the final answer to your exact differential equation. So it's a very easy procedure. If you're not able to identify what phi is, then you can adopt this procedure. Now the proof of this rule which helps you to solve exact differential equations requires a little bit of knowledge of the theory of differentiation, especially partial differentiation. So we are not discussing that right now. It's this video is dedicated towards learning techniques of solving exact differential equations without going into the details. So let's look at some problems. Let's look at this question. Suppose the question asks you to solve let's say 6xy minus y cube dx plus 4y plus 3x square minus 3xy square dy equal to 0. Now this is a long expression. M happens to be this, n happens to be this. The equation is already in the form m dx plus n dy equal to 0. So you are always prompted to check exactness whenever the differential equation of this type is given. Since exact differential equations are dealt using this alternative general form of first order first degree differential equations, so we are always prompted to check exactness whenever we encounter a differential equation of this type. Now how do we check exactness? Equality of partial derivatives. Let's check the partial derivative of m with respect to y. Please mind it that when I write this del notation, it stands for the derivative of m with respect to y, treating x as a constant. That's why this del symbol is used, because it's standing for the partial derivative. So del m by del y, so that means I am to differentiate this partially with respect to y, treating x as a constant. So if x is a constant, 6x is a constant. So the derivative will be 6x minus 3y square. That's the partial derivative of m with respect to y. Let's take the partial derivative of n with respect to x. Now when we do n with respect to x, then y is like a constant. So this term is like a constant and the derivative of constant is 0. Derivative of 3x square with respect to x, so that's a 6x, and derivative of minus 3xy square with respect to x, treating everything else as a constant. Everything else involving y or a pure constant is a constant. So it's like minus 3y square, and gives me the equality of partial derivatives, and hence my equation is exact. Therefore the given equation is exact. Now once you have the given equation as exact, there are two options available. Either you go for the hunt for phi. So there are now two options available for finding the solution. Either you go for your hunt for phi. Phi should be such that this total expression on the left hand side becomes d of phi. That is one way of handling exact differential equations. The other way is through the rule that I have taught you just above. So since this is a very big expression in x and y, m and n are a little complicated, so let's not get into the hunt for phi. Instead, let me adopt this procedure which I have told you just now to find the solution. The procedure says you integrate m with respect to x, treating y as a constant. So what is my m? M is 6xy minus y cube. So that means I am to integrate 6xy minus y cube with respect to x, treating y as a constant. So if I treat 6y as a constant, it becomes 6y, integral is x square by 2. Now y is like a constant, so this term also gives me constant times x. So that's the integral of m with respect to x, treating y as a constant. Now I have to do the second step by only concentrating on those terms of n which are independent of x, which are not involving x. Now look at my n. This is my n. This term is 4y, not involving x. This term involves x, so I'm not going to include it in n star. This term also involves x, so I'm not going to involve it. So the only term which I get in n star dy when I'm to integrate n star is only 4y. N star happens to be those terms of n which are independent of x, and 4y happens to be the only term in this question which is independent of y. So my n star dy is 4y, integral of 4y with respect to y, and that's equal to 4y square by 2. And the solution according to the procedure is given by this plus this is equal to c. So it's 3x square y minus y cube x plus 2y square equal to the constant c, which happens to be the solution. Now amusingly, the phi that you were looking for is going to be obtained in the end on the left hand side always. You can see, cross verify this, that if you do the d of this expression, then you are going to get exactly what was written in the left side of the differential equation to begin with. So your phi, if you would have gone for your hunt for phi, then phi would have been 3x squared y minus y cube x plus 2y square, and which is not very easy to identify if you do it ab initio. Hunt for phi will not be easy. So adopting this alternative procedure for solving exact differential equations is always advisable instead of going for the hunt for phi whenever your equation is a bit complicated looking. So let's do one more problem of this type and then understand this technique better. Let's look at another differential equation now. So let's look at one more example. This is the next example. Suppose you are expected to solve 2x sine y plus y cube e to power x dx plus x square cos y plus 3y square e to power x dy equal to 0. Again, as I told you that whenever you come across a differential equation in this format mdx plus ndy equal to 0, you are always prompted to check exactness. And even if it's in the dy by dx format and you want to check exactness, you can always put it in this form and then go for checking exactness. So this is my m dx plus n dy equal to 0. When I compare it with that standard form, I am able to identify my m and n. Now for exactness, what do we want? We want equality of partial derivatives. Let's check del m by del y. The function which is appearing with dx, its partial derivative with respect to y is to be taken. Now when you partially differentiate this expression with respect to y, 2x is like a constant and the derivative of sine y is cos y. And for this term, e to power x is like a constant and the derivative of y cube is 3y square. So this is your del m by del y. Let's see what is del n by del x now. For del n by del x, you have to differentiate n partially with respect to x. So cos y is like a constant, so you have a 2x cos y. And del n by del x, when you are doing, that means 3y square is like a constant. So it's 3y square e to power x, and bingo, these two are equal. So you do have exactness of the differential equation. So once you know that equation is exact, since del m by del y is equal to del n by del x, the given equation is exact. So it's just, the equality of partial derivatives which ensures the exactness of the differential equation. And once you have exactness, you have two options available. Either find the phi such that the left hand side is d of phi, which is not that easy in every problem. In certain trivial problems, it's very easy to locate, identify your phi. Otherwise, in most of the problems, the left hand side will be a little complicated looking and identification of phi would not be that easy. So it's always good to adopt the procedure of integration of m with respect to x, treating y as a constant, and then integrating the terms from n which are independent of x, and then adding these two integrals equate to the constant c to find the final answer. So let's look at our m. M was 2x sine y plus y cube e to power x. You have to do integral of m with respect to x, treating y as a constant. So y as a constant, that means 2 sine y is like a constant. Integral of x would be x square by 2. And here y cube will be like a constant and the integral of e to power x is e to power x. Now look at n star dy. Let's first see what is n here. N was x square cos y plus 3y square e to power x. So let's copy n here. N is x square cos y plus 3y square e to power x. Now by n star we mean those terms of n which are independent of x. Now this term is very much involving x because of this x square present with cos y. This term is also involving x due to the presence of e to power x. So basically your n star is 0. There is no term in n independent of x. So your n star is 0 and the integral of a constant 0 is the constant of integration c. So effectively your solution, the general solution of this given differential equation happens to be this integral added to this integral equated to the constant of integration, or the constant, whatever constant you want to name it, because one c is appearing here, there another c1 is going to appear, but since it's a first order first degree differential equation, you are going to have only one arbitrary constant in the end. So let me combine those constants to write it as some constant, say a, and that's the general solution to the problem that we began with. So exactness is a feature enjoyed by a differential equation which helps us to solve it in a very easy fashion. But before we solve it, how to ensure, see, if you are able to locate your phi, just looking the glimpse of the differential equation helps you to find out, identify what phi is, you are done. But suppose the equation is complicated looking, you will have to first verify exactness of the differential equation through equality of the partial derivatives, and once you ensure equality of partial derivatives and hence exactness, then there are two options available. Either go for the hunt for phi or adopt this alternative method which we have listed here in this video to solve any kind of exact differential equations. Finding that phi will not be a cakewalk every time, but yes, this procedure, which is an alternative procedure, is going to help you solve any kind of exact differential equation. So that is all for this video. In this we have learned exactness. In the next 2-3 videos I am going to tell you techniques where the given equation to begin with is not going to be exact, but yes, there will be some techniques which we will be learning in the next 2-3 videos which will help you make non-exact differential equations exact and then solve them the exact way. So that's the intention of the next set of videos. But for now, this is the end of this video. Thank you so much for watching, everyone. Thank you.